And we're recording. Alright, hello everyone. First things first, congratulations to John Angarita. He's about to get his PhD in aerospace engineering and move on to bigger and better things. But before he goes, he was nice enough to show me how he set up his Gazebo / ROS environment for system identification for drones. So we thought we'd put together this video / documentation to help any other prospective graduate students within the department get up and running, and if they want to take John's work and either alter it or improve upon it, this is a piece of information or a documentation that they can use to get started with. So my name is Marco Peterson. I will be walking you through the same steps that John showed me to get Gazebo up and running, and then we're going to jump over to John's machine and he's going to show you the nitty-gritty details in his Python code and how that works. So we'll go ahead and get started. So this is built for Ubuntu 18. If you're using Ubuntu 16, it will probably work, but we did not test using 16. We're currently using 18. And then we'll be using ROS Melodic and Gazebo and 9. Alright, the first step in getting the first step is installing Gazebo and ROS using the bash scripts. So for the full installation instructions, you can find it here at this URL. This hyperlink does work. This takes us to the PX4 development documentation. It's currently under Get Started Linux and Ubuntu Linux or Debian Linux. And we're looking for the subparagraph right here, which is ROS / Gazebo. So this is downloading the bash shell and then running that bash file. So I essentially took both of these command lines and just copy and paste them into the setup document. So all you need to do is either from the website or from the document itself, just copy and paste into your terminal. I've already done this, so obviously it's going to give me an error. But once you've downloaded the bash, this doesn't take very long at all, then you can go ahead and run the bash. Now this is the command line that takes forever. Again, I've already done it, so I'm going to see what happens. Yeah, it's going to ask me for a password. It's going to try to do it again. So we don't want to do that. I'm going to cancel out of that. It takes about 10 minutes to download. And the reason why it takes 10 minutes, if you want to see the full bash file, or if you're familiar with bash files, you can click it right here. So this is going to install all the common dependencies, libraries, and tools that you need for ROS Melodic and Gazebo 9, as well as MavROS. So it's a ROS Melodic Gazebo Simulator. It's going to do the command lines for you instead of you doing them each individual one inside of a terminal, which is extremely useful. It's going to set up all your keys for you with the sudo command. It's going to get ROS and Gazebo. It's going to install all those files for you. It's going to update them, and it's going to make the Catkin workspace for you. So bash files are incredibly handy, incredibly powerful. If in the future you would like to alter the bash file, or if this setup requires a library or functionality that isn't currently included, you can import that functionality or library within the bash file and then just run the bash file from there. So after you have these two done, next step is to download the PX4 source code. All that is again, it's a git clone, so just copy and paste this into your terminal. I already have it downloaded again. And then once you have that Git repository downloaded to your machine, then you're going to run its bash file. Now once you have all 4 of these lines completed, then you can go ahead and restart your machine. So you could do that one of 2 ways. Either you can go up here in Ubuntu 18, hit the power button and hit restart, or inside the command line you can hit sudo reboot your machine. Once your machine is rebooted and you're logged back into Linux, I like to do an apt-get update just to make sure everything's updated, and then we can check to see that our installs are actually there. So one of the ways to do that is by printing the environment using grep. So we're going to grep the ROS environment and show you what that looks like. So here you can see, I'll show you what our version is, what our Python version is. ROS still uses Python version 2 instead of Python version 3, so just keep that in mind. And this is also what distro you're using, in our case Melodic. Another useful thing is ROS pack find. In this case, we're going to find the ROS CPP file. So this is the directory for the ROS CPP file. So we know ROS is installed at this point, but ROSpack is incredibly useful if you want to find other things within ROS. It is a rather extensive piece of software and it has a lot of things within it. So I included the ROSpack URL here, and this is all the documentation for how to use ROSpack and all the arguments that go into finding things within the ROS environment. Another useful thing, so app cache search, what this is going to do, it's going to take a word count, that's what WC is, word count of all the files in your machine that have ROS melodic. So if we do that over here, see there's 2,950 files that have ROS melodic. Take that one step further and actually list out what those files are. You can use the dot or -n search. No! Stand by. And that'll actually list out if it'll do it. Nope. Did we freeze? Interesting. Well, I don't know what's going on with that terminal, but we're going to kill it and see if this terminal likes it. This terminal likes it. There we go. Make sure you can see the bottom of this. It likes to cut it off. Alright, the reason why this is useful, see, everything that has ROS melodic has been listed. So now you can go and find things. For example, in our case, MavROS. Make sure MavROS is installed, and there it is. We have 2 MavROS files. Or you can go in and search, make sure the Gazebo files are there, so on and so forth. If you have any other packages or libraries that you like to find or see if they're installed or what versions of them were installed, this is an incredibly helpful little command line interface. Alright, after we've checked that everything's installed, we have MavROS installed, obviously all the files are there, or at least all the ones that we're going to need. We can start running Gazebo. Now, to run Gazebo, we need 3 different terminals. Now you can either Control-Alt-T and just make a new terminal, but that takes up more screen space than is relatively necessary. You can hit Control-Shift-T to make a new tab, or alternatively you can hit just new tab. Either way you do it, have 3 tabs open. You really don't need to be inside the Kaken workspace to launch ROS Core, but to manipulate some other things you need to be inside the Kaken workspace. So to launch ROS Core in its ROS launch, you don't need to be inside the Kaken workspace, but for other things you will. So for the first terminal, go ahead and launch your ROS Core. So ROS Core, that'll get the core up and running. Alright. The reason you need 3 terminals is because, as you can see, once the core is launched, you can't do anything with it. So in order to put in more commands, you need more terminals. Oh, that put it over there. I'm going to move that guy over here. Next one, ROS launch MavROS. Copy. Alright, MavROS is up and going. And then, if you have an error when you attempt to launch MavROS, specifically this one, error cannot launch a node. This happened to me when we were trying to set up my machine for this. Just do a pip install future, and then a Kaken build to rebuild Kaken environment. And that should clear out the error. If it doesn't, either email me or John if we're still here, and we can try and find a workaround. Or if you find your own workaround, email me, Marco7 at vt.edu, and I will send you the overleaf LaTeX file that this was produced with, and you can input the fix that you found. This is 100% intended to be a living document, so if we find fixes or bugs, let me know and we'll just revise it and we'll add revisions as needed. If you want more information on this, full information for launching ROS is right here. I'm going to click on that. The same web page, just a different tab. Now we're inside Robotics, ROS, and ROS with Gazebo Simulation. So we're concerned about this one right here, which is the simulation environment. If you start launching ROS on actual hardware with PX4s and companion boards such as Raspberry Pis, or hopefully in the future the NVIDIA boards, these are the protocols and interfaces you'll be working with. Be launching and programming basic parameters and Q ground control. This is what Gustavo and Minzen do over in the Space Drones laboratory. So these are the protocols we want. Installing ROS and Gazebo, and this is the line of code that we were looking for. I just copied and pasted that down here. So this is your terminal 2. Terminal 3 is actually launching Gazebo. So in order to launch Gazebo, you do actually need to be inside the firmware directory. So just cd into firmware. For those of you that are new to Linux, cd stands for change directory. So in this case, we change directory to firmware. If I back up one, cd space dot dot. If you hit ls, that just stands for list, and that list directories are the same as folders in Windows. So these are all the quote-unquote folders that we have in the current folder that we're in, and we want to change to this firmware one. So just cd firmware, and that'll get you in there. And once you're inside the cd directory, the firmware directory, you can launch. This one is to ensure that you're in the correct path. But since we know we're in the correct path, we're already in the CD or in the firmware directory. You can go ahead and launch the entirety of this guy, and that'll get your Gazebo environment up and running. Usually there's a drone sitting here, but I've been playing. There's a quadcopter that would be sitting here, but I've been playing around with Gazebo, so it's not there anymore. So this is your good Gazebo environment. Left click will drag around. Scrolling in and out of the mouse wheel will zoom you in and out, or right click and holding will also zoom you in and out, and then middle clicking your mouse 3 button, which in most cases is the mouse wheel itself, depressing that into the mouse will pan you around. Now the reason Gazebo is such a powerful environment is because there's a lot of pre-made things inside the environment, both 3D models and the physics that go with them. One of my favorites and probably the most ridiculous is the Polaris, this guy. I don't know why somebody put a Polaris in Gazebo. I'm assuming somebody out there is driving Polarises autonomously using probably LiDAR or a Pixhawk framework in some way, shape, or form. But there it is. All the 3DR sensors you can find here. You see we've got the LiDAR, the stereo cameras, so on and so forth. Probably more analogous to our research. The basic plane is here. You can throw the plane down, and then the DJI quadcopters, you can select those. Gotta think about it. You can throw those down. So there's a lot of pre-built platforms that you can already interact with, and you can throw the sensors on top of them already. So you have the Gazebo environment up and running. We'll hop over to John's machine, and he'll show you the nitty-gritty details of his code. But before we go over there, there's an optional menu. So run a Gazebo with automated tmux file. Optional, but it's easier. So what tmux does, it's right here. Essentially, it creates terminals for you with a bunch of windows. For example, we still have terminal 1, 2, and 3. Inside of a tmux file, you can determine, like, I want to launch ROS core. It'll execute ROS core, or ROS core, and then you could tell it to hold for 5 seconds. Oh, that's Alexa going off. And after the 5 seconds, execute the next command. And then once that command's executed, you can basically time out when you want your commands to be executed, and John was nice enough to provide a tmux file to launch all of this for you. He'll explain that once we're over at his machine. But if you want to go ahead and download tmux now, you can do it right here and get it on your machine before we hop over to John's. Anyway.
Welcome everyone to my recording on how I do some of my system identification work in the Gazebo simulation environment. Today we'll just be starting with just how I get the system running. So with the document I've shared before, it'll give individual commands on how you want to run it, but I developed this short script on how I can do all the commands at once while being able to see the output in one terminal. So just to give a quick preview, you have one pane that's going to stop ROS core. A little while later, you have, after the command, mavros will launch. Afterwards, you can start the PX4 along with Gazebo. And then for my own code, I start an offboard test node. So to see this live, here's ROS core, starting the MavROS node here. And here the Gazebo PX4 will start. Just to give a quick note, sometimes this can be finicky, so if you're using a copy of this, you can adjust the sleep timers how you want, and may want to run this once or twice, but in general this does work pretty well. So give a little bit of time just so you can see this ROS run, play opens offboard test node. Here you can see the quad rotor fly. And these are the commands that I'm sending it. And if you can see, we'll look at Gazebo really quick. The quad rotor is doing a little bit of gyrating. So we're going to go ahead and kill that for now. And look at how we actually go ahead and run some of this. So this is my Python script that creates a ROS offboard node, and I want to highlight a few of the key aspects. I highly recommend going through some of this and the basic ROS scripts on publisher subscribers, along with some of the online code PX4 has, to understand a little bit more of what's happening and some of the key aspects, but I'll try to explain the most important ones here. So in this Python environment, in general, these are the commands that I'm all running, but let's look at each one individually. So first, one of the key things is being comfortable with is the actual variables and messages that you're going to have to be using when playing with the simulation. They're pretty much straightforward and quickly, and you can learn them fairly quickly. Just state, attitude, target, post stamped. And this can just be seen on the MavROS and ROS website on what they mean and what details you'll need to know for them, but it's fairly straightforward. I won't take the time here to explain through it. The important aspect that really needs to be understood well is the publisher subscriber aspect, what I call set pub sub here. So the two key aspects that I would want you to take away from this video are understanding what exactly is happening with publisher and subscribers, and where is this information going and where are we retrieving it from. So first, talking about the publishers and subscribers. First, we have a couple publisher lines here and here, and what they're doing is publishing a value. For this one, a position target. This one, post stamped and thrust. Publishing certain values to these locations that we'll explain a little bit more later. And in a similar vein, we have to enable a subscriber to get different data from these locations. Subscribers are a little bit different because you need to specify the data that you're looking for, and also one function that you're going to be using for that data. So essentially what these last two do is save the data that I get of this type from this location to just another variable. Or you can go ahead and define it in a different way, but that's really up to the user. So one of the more confusing aspects that may take some time to look at is understanding these locations. So to give just a quick background, MavROS is the ROS implementation of sending mavlink messages to quad rotors, where mavlink messages are typically how they talk and communicate with their needed information. So in order to really engage with the quad rotor in simulation, you need to make sure you're publishing to the right location, and each one of these can be a little bit unique, such as in general MavROS set point Yeah, mavros set point position local. You're actually just going to be taking the yaw value in the pose, and that's what it's going to be trying to perform. So there's little quirks to each of these, and you can further adjust them with what they call masks to further really have these do what you want them to do. I highly recommend looking at the mavros website. Then ROS, I should have one open. Specifically, we look more at set point positions and set point raw. And here you can say, and here it explains what exactly it's doing. Usually the message type. And just getting a little bit comfortable with this is fairly important. So these are the typical publisher inscribers that you need to enable to actually send and get back data. Next important aspect that I have, at least in this section of my data, is also setting servers for the next important aspect of flying the quadrotor, getting into offboard mode, and arming. So specifically with the setup that PX4 has, you need to arm it by sending a boolean to this location, and here you can set the specific flight mode that will be set to offboard a little bit later on in the code, but I find it important to go ahead and establish that here. In order to actually armed and switch to offboard, you need to have some waypoints published to the quadrotor already. So we can go ahead and jump to this line that I call set prelim points. So a very basic point that I decided to use is just 2 meters up. Here I had commented out just some yaw positions that just testing capabilities. If you want, you can go ahead and use that, but this is just basically what I have it first commanded to. So my version of the code runs a little bit differently, where yes, I have this point, what I call desired pose, published with this line. Pose pub, which is the line we had before that activates your publishing ability. And this part here will actually go ahead and publish the point, desired pose, that I have defined here. So I have it published just the same point about 100 times. This can be adjusted however you want. But the main difference between my code and some other examples you may see is that I actually have this particularly threaded so that it can be consistently publishing points while it tries to arm itself, while it tries to go into offboard mode. Otherwise, it can be a little bit difficult to handle some of the points. It may try to change it to arming, it may try to change it to offboard. While these points have finished, it can be a little bit finicky in that aspect. But this is what I found to work most consistently for me. I definitely recommend looking at some of Colin's code if available to see a little bit of a different way to go about it. So looking just quickly about specific lines on how to go to offboard and how to go to arming. This is the section where I go to offboard, and to super quickly break it down, I just have multiple loops where I attempt to set it to offboard. Here is the line, is self.state.mode equals desired mode. In this case, offboard is true, set mode success. If not, I try to publish to the server my desired mode. And like I said before, this is usually in conjunction where I specify offboard. So this just loops for a couple seconds until it gets it to offboard. Like I mentioned before, Colin has a little bit different version of getting to offboard, which can be seen here. And ultimately the difference is this is just constant looping, and it's more so I've added a failsafe method in this case. So the arming is set in a very similar way. If self.state.armed equals arm, where arm is a boolean that should ultimately be set to true, hey, you're done. Set arm success. If not, then try to, once again, to set arming server, set it to armed, in this case true, and there you go. And with the threaded waypoints, it should go ahead, be armed and off board. So I'm just going to explain one of the more basic flights. So before I had, like I mentioned before, just constantly publishing desired pose, and since I haven't changed it, the key aspect right here is while not ROS-Pi shut down, i.e. until ROS-Pi, as long as ROS-Pi is still open, is going to keep attempting to publish this point. It'll essentially keep flying. Another key aspect is self.rate.sleep. Basically, at the publishing rate that you want, you should very much include this to make sure it's not over publishing. Like, this can go extremely fast, but having the sleep command, you're having it stay at the rate that you want. Specifically, in this one basic case, I had some hard code tested for 30 to make sure it's publishing at 30 Hertz. But just to give a little bit of background of how my system identification threaded flights run, is once it actually reaches that initial specified point that's publishing really well, I start a new section of the code called engage flight inputs, which is happening here. And essentially what that is just doing, it's just pulling from a separate text file here, reading the first line, and then trying to publish that line and publishing at a matching rate that is specified before. So one other aspect that I want to go over is a little bit of some of Colin's old code, which is a little bit simpler in implementation of trying to make it go a certain path. Once again, using publisher and subscribers, you can subscribe to your local position to get data. And this example, you save that local data here. And then by publishing the same command up until you reach that point, you can have it match a trajectory, i.e. it will keep publishing the first point with this line. It'll attempt to get there, and once it gets there, it'll switch to the next line, i.e. the next point in the trajectory. And it'll keep doing this until it's reached the end of the code. So that's usually the more straightforward way of publishing trajectories. But because mine, I want to publish at a certain rate, mine's implemented in a fairly different way. So overall, I hope this video helps explain some of the key aspects of running Gazebo. And just as a little added bit, you just see it run again. See some of the aspects being spit out while I'm running this. Alright, thanks again for watching.